Lesson 3.3, Rates of Change and Particle Motion. Suppose that the amount of air in a balloon at any time t is given by V of t equals 6 cubed root of t over 4t plus 1. Determine if the balloon is being filled with air or being drained of air at t equals 8. How do you know? So we want to know, is it being filled or drained? So this is a volume. So filled would be the volume is increasing. Drained would be the volume is decreasing. At t equals 8 means let's take the derivative of v, plug in 8. If the derivative at t equals 8 is positive, then the volume is increasing. If the derivative is negative, then the volume is decreasing. So v prime, low, v high. On the top, that's going to be 6 times 1/3 t to the negative 2/3 minus high v low all over low squared. All right. I notice right here, the 6 times 1/3, I'm just going to rewrite that as a 2 for simplicity. Now, I could go through and simplify this, or I can just go ahead and plug in 8, because the question is not what is the number. The question is this positive or negative? So just to help me keep track, I'm going to do, I'm going to plug in 8. Now, right here, when I plug in 8, I'm going to recognize that e to the negative 2/3 is a fraction. The 1/3 part of the 2/3, that's a cube root. The cube root of 8 is 2. 2 squared is 4. So that's really a 1/4 minus 6 times, that's going to be 2 times 4 all over 4t plus 1 squared. Again, the question is this positive or negative? The bottom, that's 32, 33 squared, that's a positive value on the bottom. So I don't really care about the bottom. On the top, is it positive or negative? Well, this is 33. 2 times 1/4 is 1/2. Half of 33 is a positive number. This is 12 times 4 is 48. Well, if I take half of 33 and subtract 48, that's going to be negative. So I know that v prime of 8 is negative. So the question is, determine if the balloon is being filled or drained at t equals 8. Balloon is being drained at t equals 8 because v prime of 8 is negative. Final answer. Now, while we're on these application problems, as is always the case, I want you to solve the problem by hand and then check your answer with a calculator. With these, I'm actually going to go ahead and check the answer with the calculator with you just to make sure that we're using the appropriate techniques. So here I've got the function typed into the y1 on the calculator. If I go to show the graph, I see something like this, but I honestly don't even really care what the graph looks like. I just want the derivative at t equals 8. So I can do this 2 ways. I can do it from the graph, second calc, option 6, and then input 8. And I get my output of negative who cares, because I don't care what the number is, I just care that it's negative. So I can immediately just jump to, without writing anything down, if this is a calculator question, my full incomplete response would be that V is being drained because V prime of 8 is negative. Again, if this is a calculator question, I don't need to show any work. I can simply respond with this statement right here, illustrating that I understand that it's being drained because the derivative is less than 0. I don't need the graph. I can do this from the home screen entirely. So if I do math option, I believe it was 8, if I remember correctly on the TIs, So math option 8, I've already got the function typed in. Actually, let's do our variable. I can retype the function here, or since I've already got it for y1, I can type alpha f4 on the 84s, and then I want to select option 1, and then evaluating at 8. So I get that same decimal answer, but again, v prime of 8 is negative is all I really need to know. Suppose that the amount of water in a holding tank at t minutes is given by v of t equals 2t squared minus 16t plus 35. Let's start at the beginning. Is the volume of water in the tank increasing or decreasing? So volume is increasing would mean v prime is positive. Volume is decreasing, v prime is negative. So let's do this by hand. V prime of t equals 4t minus 16. So v prime at 1. 1 times 4 is 4. 4 minus 16 is definitely a negative number. So I just care that it's negative. So I'm going to say volume is decreasing at t equals 1 because v prime of 1 is negative. And just like before, I can type that function into my calculator and then either use the graph or the inderivative function from the home screen to calculate the derivative using the calculator just to get the negative number. I'm not going to read it here. Part B, same question, but at t equals 5. V prime is already known to be 4t minus 16. V prime of 5. If I plug in 5, that's going to be 20 minus 16. That's going to be a positive number. So volume is increasing at t equals 5 because v prime of 5 is positive. Part C is the volume of the water changing faster at t equals 1 or t equals 5. Let's pay attention to that word faster. Anytime I use the word fast or slow, those are references to speed. Speed is the absolute value of velocity. So if I have a velocity of -4 and a velocity of +1, and I ask you which one is going at a lower velocity, -4 is a lower velocity. Versus if I say which one is going slower, well, slower ignores the positives and negatives. -4 becomes +4. 1 is still 1, so a +1 is a slower speed than -4, whereas -4 is a lower velocity. So when I see that word faster or slower, we need to pay attention to the magnitude of the value, not the sign of the value. So t equals 1 and t equals 5, those were the values from the previous two questions. So I know that v prime of 1, if I go back, I know it's negative, but now I actually care that it was -12. And v prime of 5 was 4. But the speed at 1 was actually 12. The speed at 5 was actually 4. Which one is changing faster? The one that's changing faster is the larger magnitude. So the volume is changing faster at t equals 1. And then part D is the volume of the water in the tank ever not changing. Well, the volume would be not changing if the derivative equals 0. We know the derivative is still 4t minus 16. And that's going to be 0 at t equals 4. So is the volume of the water in the tank ever not changing? Well, at t equals 4, volume is not changing at p equals 4. Suppose that the amount of money in a bank account is given by p of t, where t is in years. The graphs of p, p prime, and p double prime are given below over the intervals 0 to 7. So keep that in mind, 0 to 7. So that means this endpoint right here is at t equals 7. During the first 7 years in which the account is open, when is the amount of money in the account increasing? When is the amount of money increasing the fastest? So let's start with strictly increasing. So P of t is the amount of money in the account. So P of t is increasing when P prime of t is positive. So I can look at P prime of t and see that P prime of t is positive from B to D and then from F to 7. Now, of course, that could also have been answered directly from P of t, increasing from B to D and from F to 7, both of which give me the same result. So increasing, P is increasing on B to D, union F to 7. So I just wanted to give you two different ways of answering that question so that we can see that we get the same result, whether we look at the function P or P prime. Next, let's look at the second question. When is the amount of money increasing the fastest? Increasing the fastest. There's that word again about fastest, which has to do with a speed, not necessarily just a rate of change. So it could be a positive rate of change or a negative rate of change as long as it's steep in the positive direction or in the negative direction. So we're talking about the amount of money increasing. Well, the amount of money is increasing on this interval right here. Where is it increasing the fastest? Well, that would be where the rate of change of this interval has a maximum. Well, that's where P prime comes into play. The rate of change of this interval has a maximum at point C. You may also notice that at point C, the second derivative is equal to 0. Increasing to the fastest is just another way of saying a point of inflection. That particular phrasing is going to come back a few times throughout the course of this year. When is a function changing the fastest? That's a point of inflection. The point of inflection for this graph, since we're strictly talking about on intervals of increasing, would be at point C. Now, technically, you could also make an argument about t equals 7 as well, because if this graph were to continue following its same pattern, I would assume that t equals 7 is also a maximum, but since I don't know what's happening to the right of 7, I'm going to exclude that from consideration. So the amount of money increasing fastest at t equals c. So all that discussion about speeds and velocities leads us into one of the most common calculus applications of rate of change, and that's particle motion. Particle motion, or a discussion of position, velocity, and acceleration. In calculus, we often will describe the position function as s of t. S of t is not a standard label for position. It is a very common label for position, though. If you don't have a label for position, I recommend just use S of t for position. D of t is also common, X of t, Y of t, P of t. And we're not very standardized when it comes to the label for position. Now, the rate of change of position, that's called velocity. Now, velocity, we do have a standard label for, and that's v of t. Anytime it's velocity, label it v of t. If we take the second derivative of position, which is also known as the first derivative of velocity, the rate of change of velocity is called acceleration. So position, velocity, acceleration. The rate of change of position, how much is the position, or how fast is the position changing? That's called velocity. Well, how fast is the velocity changing? That's acceleration. Paying attention to units, if I tell you that position is in meters, and let's say that time is in seconds, the velocity, since velocity is the change in position over the change in time, that would be meters over seconds. Hence, velocity would be meters per second. Meters for position, meters per second for velocity. Well, acceleration is the change in velocity over the change in time. If velocity is meters per second and time is seconds, that would be meters per second, or meters per second squared. Anytime we have position, velocity, acceleration, and you're told to include units, pay attention to your unit for position, pay attention to your unit for time. Position is position over time, or position is position, velocity is position over time, acceleration is position over time, or position over time squared. Now, of course, the absolute value of velocity, as we've already talked about, that's speed. Here's a little chart of the vocabulary that we can use for position, velocity, acceleration, and the relationships to each other. Notice here I have position, velocity, and acceleration. Position is like, you call it the zeroth derivative. First derivative is velocity, second derivative is acceleration. Position, here I have my unit in meters. Velocity, this is just a weird way that British people write their units. Instead of saying meters per second, they'll say meters s to the -1, which is just ridiculous. But that's why we fought a war. Acceleration, meters per second squared, which is the rate of change of velocity. Now notice, as you can see, we could keep going where the rate of change of velocity, we actually call that jerk. If I have a sudden change in acceleration, that's the jerk. The third derivative of position is called jerk. And then the fourth derivative, some people will call it jounce. No idea what that word is supposed to mean. But the cooler people will call it snap. So a sudden change in jerk is a snap. And then a fifth derivative, crackle. And then, yes, mathematicians have jokes too. Pop, and then lock, and then drop. So position, velocity, acceleration, jerk, snap, crackle, pop, pop, lock, drop. Now, FYI, this is just kind of a joke. There really isn't, because we live in a three-dimensional spatial universe, there's not a lot of physical applications or representations of these. It's more of a theoretical study in rates of change. So what you call them, it really doesn't matter. This is just what a lot of the cool math and physics people will call it. Same thing as we integrate up, which we'll be talking about later in the course. If I integrate position, we call that abscessment, then abscity, then abceleration, abcirc, absounce, because you can kind of see the inverse relationship versus the derivatives. This abscessment and abscission, that has just to do with combinations of words. Abscission has to do with the absolute change in position. Abscessment based on absolute change in displacement. Abscity, absolute change in velocity. Acceleration, absolute change in acceleration, and so on and so forth. Don't worry, we are only focusing on this. All right, what we want to do on this slide is kind of match up some vocabulary with some mathematical notation. One of the most common mistakes that students make has to do with a misrepresentation of what is said verbally by using improper notation. A lot of times you can earn points on a free response question simply by translating the English statement into a mathematical statement correctly. That can often be the first point in a problem. So here we have a bunch of verbal statements and some mathematical statements, and your job is to match these up. If you are working off of the Desmos activity, this is a self-checking activity. So as you match up the cards, it will tell you right up top whether to keep trying or whether it is correct. Keep in mind that it is not necessarily a one card to one card correct. There could be multiple cards that match together, so make sure that you're paying close attention to that. Make sure you try this on your own, and if you get stuck, you can hit play for me to go over it. All right, so I'm just going to start jumping in here. So here I have the speed of an object is 3 meters per second. So speed is the absolute value of velocity. So I want s prime, but I want an absolute value around s prime. And the speed is 3 meters per second, so it's not time is 3, it's the output is 3. So I'm looking for, oh, here we go. I'm looking for the derivative, absolute value of the derivative is 3, so we can put those together. All right, let me go ahead and close that to save space. The object is moving up at a rate of 3 feet per second. So 3 feet per second, that's a velocity. Object is moving up, so it's a positive 3 feet per second. So I need a velocity equals 3 feet per second. So I'm looking for S prime equals positive 3. That would be right here. S prime equals positive 3. Let's pair those together. The object hits the ground. The object hits the ground. So if the object hits the ground, then its position is 0. Position is 0. That would be over here. Find the average velocity of the particle. So an average velocity would be an average rate of change of position. So average rate of change of position, that's going to be this guy right here. There's our average rate of change formula, y2 minus y1 over x2 minus x1. Anytime you see the word average rate of change, you're looking for the algebra 1 slope formula. All right. Object is 3 feet left of the reference point. So we're talking about the position of the object, S. The object is 3 feet to the left, so S is negative 3. S is negative 3 right here. Find the velocity as time increases without bound. Increases without bound, that's to infinity. Time is going to infinity for the velocity, so that would be the limit. Here I have a limit, but that's a limit of position. I need the limit of the velocity. Oh, that would be down here. All right, let's kind of move some of these out of the way. All right, let's see. Find the highest position. Find the highest position. So the highest position, so here I have a position, but this isn't highest because highest would be going up and down. This would be going to the right. This would be the rightmost position. The highest position is going to occur, that's a maximum. Well, a maximum occurs when the derivative equals 0. So I'm going to put those together. Object is moving left or down. That would mean the velocity is negative. So S prime of t is negative. Find the time when the object turns around. Well, the object turns around, the velocity changes direction when the derivative equals 0. That was this guy right here. So I'm going to put those together. Let me put all that together. Object is at rest. Oh, that's the same thing. So all of this says the same thing. And look at that. We've got our final answer. All right, so before we continue with the main activity, let's do a little bit more practice with these particle motion type questions. To the right, you have a graph that represents time versus velocity. Notice that this is the velocity function. Assume that the positive direction is to the right. So the original particle is not moving up and down. It's moving to the right for positive, left for negative. Go ahead and try these on your own. Hit play when you're ready. When is the particle moving at a constant speed? The particle is moving at a constant speed when the velocity is horizontal. So that would be right here from 0 to 1. When is the particle moving to the right? The particle is moving to the right whenever the velocity is positive. Velocity is positive on this interval right here from 0 to 2. When is the particle moving to the left? Particle is moving to the left when the velocity is negative. The velocity is negative from 2 to 5. Here are a few more. Pause here, play when you're ready. When is the particle's velocity increasing? Again, this is the velocity graph. The velocity is increasing on this interval right here from 3 to 5. When is the particle's velocity decreasing? That would be on this interval right here from 1 to 3. So next we have when is the particle speeding up or slowing down? Remember, speed is the absolute value of velocity. So if I have a velocity graph that looks like this, notice that for this interval right here, the velocity is decreasing. So we would say that the object is slowing down. We start with a positive velocity. Here we have a smaller positive velocity. Here we have a smaller positive velocity until right here we have a velocity of 0. Well, after we pass this point where the velocity is 0, now the velocity is -1, -2, -3. The magnitudes are now increasing. So we would say that we're actually speeding up until we get to this point, which is our maximum velocity in the negative direction. And then those speeds start approaching 0 again. So we're slowing down until we get to 0, and then we're moving away from 0. We're speeding up. So notice as the velocity graph, as the velocity approaches 0, we're slowing down. As the velocity moves away from 0, we're speeding up. We can also think of this in terms of acceleration. Velocity for this first interval, the velocity is positive, but the acceleration is negative because along this entire interval, the velocity is decreasing, so the acceleration is negative. So what we end up having is a situation where if the velocity is positive, but the acceleration is negative, then we're slowing down. Notice likewise, here the acceleration is positive because the velocity function is increasing. Well, down here, the velocity is negative, yet the acceleration is positive. So we're also slowing down. Speeding up is when both the velocity and the acceleration are negative, or both the velocity and acceleration are positive. So if we have the same sign on both velocity and acceleration, we're speeding up. If we have different signs, then we're slowing down. Let's summarize that. Speeding up, velocity is moving away from 0. Slowing down, velocity is moving towards 0. Notice here is the same velocity graph, but it's the absolute value, so anything that was below the x-axis just gets flipped up. Speed decreasing, speed increasing, speed decreasing, speed increasing. Or we can simply say that speeding up, velocity and acceleration agree. Slowing down, velocity and acceleration disagree. So going back to this, when is the particle speeding up? Particle is speeding up anytime the velocity and acceleration agree, or if you're looking at a graph, if we're moving away from 0. So here I'm moving away from 0, and that would be it from 2 to 3. Notice that the velocity is negative and the acceleration is negative because it's pointing down, so velocity and acceleration agree. When is the particle slowing down? That would be anywhere that the graph is approaching 0, so that would be right here and right here. We have a positive velocity but negative acceleration. We have a negative velocity but a positive acceleration. Velocity and acceleration disagree, so that would be from 1 to 2, union 3 to 5. Let's keep going. How fast is the particle moving at t equals 4? T equals 4 is this point right here. How fast is the particle? So that's a speed. And in what direction? Now, by observation, it looks like the speed is -5, but I don't want to automatically assume that it's -5. I can see that this is linear. I can see that this point is at 3, -10. I can see that this point is at 5, 0. If I go up 10 and over 2, the slope is 5. So if I go up 5 over 1, yeah, so I'm happy with saying that v of 4 is -5. V of 4 is -5, so that means the speed is 5. But the direction is going to take account the velocity, and the velocity is negative. Since positive is to the right, we're moving at 5 feet per second to the left. What is the particle's velocity at t equals 4? Again, we already answered that. The velocity at 4 is -5, -5 feet per second. When does the particle change direction? The particle changes direction. Let's see, at t equals 2, we go from moving to the right to moving to the left, and that would be it. Particle changes direction at t equals 2. Over what time interval does the particle have positive acceleration? Positive acceleration would be when the slope is positive. So this is velocity. So positive acceleration would be from 3 to 5. Over what time interval does the particle have negative acceleration? That would be anywhere it's decreasing from 1 to 3. Now on this one, I might be willing to say, well, at t equals 2, we have a cusp. So that means the derivative actually does not exist at t equals 2. So can you really say that the acceleration negative at t equals 2? So I would say this is probably a fine answer, but if you wanted to break this in to 2 intervals, that would also be fine. State on the interval of time when the particle has positive acceleration but is slowing down. So we want positive acceleration, which is this interval right here, but is slowing down. Slowing down is when we are approaching 0, so that would be that entire interval from 3 to 5. Here we have a similar question, state an interval when when the particle has negative acceleration, which is this interval right here, but is speeding up. Speeding up is moving away from 0, so that would only be from 2 to 3. What is the particle's acceleration at 3.5? So 3.5 is right here. I want to know the acceleration right there, so I need the slope of that line. We actually calculated that earlier. The slope was 10 over 5. So along that entire interval, the slope is 2. So the acceleration at 3.5 should be 2. What is the particle's average acceleration over the entire 5-second time interval? We're looking for the average acceleration. So as soon as I see average, I'm thinking average rate of change. Keep in mind, this says average acceleration. So if I think of average rate of change as average velocity, well, I would get average velocity by doing the change in position. So I would do average acceleration by doing the change in velocity over the 5-second interval. So v of 5 is 0 minus v of 0 is 5 over 5 minus 0. That would be -5 over 5 or -1. Particle moves along a horizontal line according to that function where s of t is position and t greater than or 0 in seconds. Find the acceleration when the particle is at rest. So particle is at rest when the velocity is 0. So let's do velocity is the derivative. So that would be 6t squared minus 18t plus 12. That equals 0. I can divide everything by 6. And then factor that into -2, -1. So t equals 1 and 2. Particle is at rest at t at rest. At t equals 1 and t equals 2. Find the acceleration when the particle is at rest. So the acceleration at 1 and the acceleration at 2. So I need the acceleration function. Acceleration is the derivative of velocity. So go back to the velocity function. Don't take a derivative of this. Take a derivative of this. So acceleration would be 12t minus 18. So plug in 1, 12 minus 18, that's negative 6. Plug in 2, that's 24 minus 18, which is going to be positive 6. So a of 1 is negative 6, a of 2 is positive 6. Part B, find all t where the position is increasing. The position is increasing when the velocity is positive. So let's take that velocity function that we found a moment ago, which again was 6t squared minus 18t plus 12. I want to figure out where it's positive, so I need my critical numbers. I've already done that. Critical numbers were 1 and 2. I don't have to re-show the work. Once I've already shown it in part A, I can just pull that data in part B. But now I need to know where the velocity is positive, so let's do a sign chart. And I'm going to put the two factors, t minus 2 and t minus 1, on the side. So at 1, t minus 1 is equal to 0 at 1. It's positive to the right. It's negative to the left. T minus 2 is 0 at 2. It's positive to the right, negative to the left. Put it all together. It's going to look like that. I want to know where for all t where position is increasing. That would be to the left of 1 and to the right of 2, but we need to be careful about to the left of 1. Because of this statement right here, t is greater than or equal to 0. I have a hard break at 0, so the answer to the question, position is increasing on 0 to 1. Now, because at 0, that wasn't a position or velocity of equaling 0. That's a positive velocity. So I'm going to write this as a bracket, union 2 to infinity. On the AP exam, again, I've mentioned this before, probably not going to be a big deal whether that's a bracket or a parenthesis, but technically it should be a bracket. Also, let's not make the assumption that just because we're talking about time that we had to stop at 0. There is no rule that says you can't have negative time. I see that when grading AP exams over the summer. Oh, you can't have negative time. Sure, you can. Negative time just means before now. Time did not start at the moment of your birth. Time did not start at the moment it is right now. Negative time just means the past. Whatever the 0 reference point for time is, negative time is perfectly fine. So I'm only going to make that restriction because it explicitly said it in the problem. Part C, find all t for which the velocity is increasing. So velocity is increasing would mean the acceleration is positive. So we're going to do basically the same thing that we just did here, but now we need to do it based on acceleration. So pulling the velocity function, actually, we already did the acceleration function earlier. Acceleration was 12t minus 18. Critical number would be 18 over 12, which of course is 9 over 6, which of course is 3 over 2. No shame in taking multiple steps to simplify a fraction. Sign chart. 3 over 2, this is going to be positive to the right, negative to the left. We do have a hard break at 0 based on that domain restriction, but we want positive acceleration anyway. So velocity increasing on 3/2 to infinity. Is the particle's distance to the origin increasing or decreasing at t equals 4? So distance to the origin at t equals 4, if I consider a number line, again, we're starting at 0, 1, 2, 3, 4. So since the horizontal is time, let's talk about up and down representing distance to the origin. So if the object is moving up, then we're moving away from the origin. If we're moving down, then we're moving towards the origin. But keep in mind, that assumes that we started with a positive position. If we started with a negative position and we're moving up, then we're moving towards the origin. So we need to be careful with how this question is phrased. Is the particle's distance to the origin increasing or decreasing? That's going to depend on not only is the velocity positive or negative, but also is the position positive or negative at t equals 4. So let's start with the position. At t equals 4, S of 4. Now, you would never be asked to do this by hand. Feel free to use your calculator. I'm going to do this by hand just to show off because I don't really care what the number is. I just care is it positive or negative. I know that 4 cubed, that's 64 times 2, that's 128. Minus 4 squared, that's 16. 16 times 9, that's 144. So right now I'm at a negative value. 12 times 4, that's 48. I know these two numbers added together are going to be more than 144. Minus 40, so if I think of these two numbers, that's just going to be 8. Added to 128, that's not going to be bigger than 144. So I know that S of 4 is negative. Now, if I consider the velocity, well, we already determined actually the velocity is positive. At t equals 4, the velocity is positive. So what we have is the position is negative and the velocity is positive. So the position is negative and the velocity is positive. That means that the particle distance to the origin is decreasing because we have a disagreement in the velocity and the position. So that means our distance is decreasing. Find all t for which the speed of the particle is increasing. So speed is increasing, so speeding up, that means the velocity and the acceleration would have to be a double positive or a double negative. I've already done sign charts for both. So here was my sign chart for acceleration. Actually, let's just copy that. So 3/2. For acceleration. And then for velocity, it was at 1 and 2, positive, negative, positive. Positive, negative, positive. So I need intervals where I'm either a double positive or a double negative. So a double positive from 2 to infinity. And then I would be a double negative between 1 and 3/2. So we've got particle, so speed increasing on 1 to 3/2 and 2 to infinity. Suppose that the position of an object after t hours is given by g of t equals t over t plus 1. Is the object moving to the right or to the left at t equals 10? Again, we could just use the calculator to test the value of the derivative. If the derivative is positive, or object is moving to the right. If the derivative is negative at t equals 10, the object is moving to the left. If you're comfortable doing this by hand, then feel free to practice with the calculator. If you're comfortable with the calculator, feel free to practice this by hand or, do both. So the derivative, low d high minus high d low, all over low squared. So that's going to be t plus 1 minus t on the top. So that's just going to be 1 over t plus 1 squared for the derivative, and I'm going to notice this is always positive. No matter what the t value is, t plus 1 squared will always be positive. A positive over positive is always positive. Is the object moving to the right or to the left at t equals 10? No matter what number I plug in, it's going to be positive. So the object moves to the right. Does the object ever stop moving? Again, the derivative is always positive. It never equals 0. Does the object ever stop moving? No, because g prime of t never, ever equals 0. Suppose that the position of a particle is given by s of t equals t e to the t. When is the particle at rest? So particle is at rest when the velocity equals 0. So let's find the derivative. First times the derivative of the second plus second times the derivative of the first. Set that equal to 0. I can factor out e to the t. So e to the t never equals 0, but t plus 1 would equal 0 at -1. When is the particle at rest? The particle is at rest at p equals -1. Again, a negative time is perfectly fine. There's no reason to ignore negative time. There are no domain restrictions expressed in this problem. So t equals -1 is my answer. The position of an object at any time t greater than or equals 0 hours is given by s of t equals that. Let's start by finding the velocity and acceleration at any time t greater than or equal to 0. At any time t greater than or equal to 0 that's just restating the domain that we were already told previously. I'm looking for the velocity at any time t. So I'm just going to state the velocity function in terms of t. So that would be 6t squared minus 42t plus 60. So there is my final answer for part A. And then for the acceleration would be 12t minus 42. Final answer. Part C, determine when the object is moving to the right or moving to the left. So moving to the right, v is positive. Moving to the left, v is negative. So let's use our velocity function, which we just got on the previous part, and do a sign chart. Be less than 0. So set this equal to 0. So let's divide by 6. I'm going to get t squared minus 7t plus 10. And then we can factor it to get our critical numbers. So that'll be factors of 10 that add to -7. That would be -5 and -2. So t equals 2 and 5. Set up a sign chart for 2 and 5. I've got two factors, t minus 2, t minus 5. t minus 2 is 0 at 2 and positive to the right, negative to the left. T minus 5 is 0 at 5, positive to the right, negative to the left. Let's not forget about our domain restriction. We have a hard stop at 0. So from 0 to 2, positive, negative, positive. The question is moving to the right, moving to the left. So we are moving right from 0 to 2, union 5 to infinity. Same issue that we had previously at 0. At time 0, the velocity is positive, so it is moving to the right at 0. And then moving to the left from 2 to 5. All right, part D, what is the velocity when the acceleration is 0? When the acceleration is 0. So I need to figure out what time that is and then plug that in to the velocity function. So we know that our velocity function was 6t squared minus 42t plus 60. We know that our acceleration function was 12t minus 42. So I need to know, when is the acceleration 0? That's going to be at 42 over 12. I'm going to reduce that to 21 over 6, which could also be reduced if I divide by 3. That's going to be 7 over 2. So then I want the velocity at 7 over 2, which would be 6 times 7 over 2 squared minus 42, 7 over 2, plus 60. Keep in mind, if this is a free response question, don't you dare simplify anything. Just leave it like that. If it's free response, you get points for a correct answer. You don't get points for correctly simplifying the correct answer. If it's multiple choice, we need to be able to simplify that to match one of the 4 answer choices that are given. So I'm going to go ahead and run through it. So I'm going to have 49 over 4 times 6 minus, I'm going to go ahead and divide by 2, and I get 21 times 7 plus 60. Of course, if I have a calculator, I'm just going to type this in, but let's pretend I don't have a calculator. I'm going to do this strategically. I know I can reduce a little bit further here, divide that by 2 and divide this by 2. I get 3. And I'm going to notice, just to try to make things easier on myself, I notice this 49 right here. Well, there's a hidden 49 right here if you see it. 21 is 3 times 7. So that means there's really a 49 right here. All right, so we have essentially 3 halves times 49 minus 3 times 49. So 3 halves minus 3, that's 6 halves. So if I pull the 49 out of these two, I get 3 halves minus 6 halves, which is negative 3 halves, and I have 60 left over. I'm going to go ahead and make that 60 into a 120 over 2. So this is now negative 3 times 49 plus 120 over 2. 3 times 50 is 150, so 3 times 49 is 147, plus 120 over 2, so that's 27 apart. So that'll be negative 27 over 2 is my velocity. Finally, at t equals 4, is the object speeding up or slowing down? It's going to have to do with the relationship between the velocity and the acceleration at t equals 4. So I need to know about v of 4. I need to know about a of 4. I don't care what the actual values are. I just care, is it positive or negative? Well, if we back up a little bit and look at our velocity sign chart, at 4, the velocity is negative. And for acceleration, we know that the acceleration function was 12t minus 42. If I plug in 4, 12 times 4 is 48. 48 minus 42 is going to be a positive number. So since the velocity is negative and the acceleration is positive, those disagree. So we're going to be slowing down. So at t equals 4, the object is slowing down at t equals 4. Particle moves on the x-axis so that its position at any time t is given by x of t equals that, where x is measured in meters, t is measured in seconds. Notice any time t, there's no restriction to our t interval. Find all values of t for which the particle is at rest. Particle is at rest when the velocity equals 0. So v of t is our derivative, or 4t squared minus 18t plus 18. Let's set that equal to 0. I can divide everything by 2. Factors of 18 that add to negative 9. Factors of 18 that add to negative 9, that would be negative 6 and negative 3. So this would be t minus 3 and 2t minus 3. So t equals 3 and 3/2. So the question was find all values of t where the particle is at rest. So at rest, at t equals 3 and 3/2. Part B, find the speed of the particle at the moment that the velocity is not changing. Velocity is not changing. The velocity is not increasing. The velocity is not decreasing. Velocity is not changing would mean the acceleration is 0. And then I want to find the speed of the particle at that moment. So let's recall that our velocity function was 4t squared minus 18t plus 18. And that would make our acceleration function 8t minus 18. So let's set that equal to 0. T equals 18 over 8 or 9 over 4. And then we'll take that and calculate the velocity. So v of 9 over 4 would be 4 times 9 over 4 squared minus 18 times 9 over 4 plus 18. Let's clean this up. Now keep in mind, we're actually looking for the absolute value of this. When I take the absolute value, that does not mean that I'm just going to change each term to positive. It means order of operations, let's evaluate the inside, and then whatever the output is for that expression, make it positive. So I'm going to go ahead and cancel out one of these 4's. So that would actually be 81 over 4 minus 18 and 4. That would be 9 times 9 over 2 plus 18. So that's just 81. And then I'm going to recognize, if I multiply top and bottom by 2, I got 81 over 4 minus 2 81s over 4. So this becomes negative 1 times 81 over 4, or just negative 81 over 4, plus 18, which is really 18, 36, 72 over 4. So that is 9 apart, so negative 9 over 4. So the velocity at 9/4 is negative 9 over 4. The speed then would be positive 9 over 4. Final answer.